All right, let's take a look at these examples. I'm going to do this a little bit differently. You can see that examples 1 and 4 both have answers. So I'm going to leave those as practice problems for you if you want to try them and see if you can match the answers. To refresh your memory from chapter 15 to see how this goes, I'm just going to do questions 2 and 3 and take you through those guided examples here in this particular part of the video. Here we have 3.65 grams of solid HCl, and it's dissolved in 2 liters of water at, pure water at SATP. We want to figure out the hydronium and the hydroxide ion concentration. So, remember from Chem 20 that our 6 strong acids, HCl being one of them, ionize completely with water to produce the brand new ions of hydronium and the associated anion, in this case chloride. Alright, so we're going to be able to get a couple of things from stoichiometry, but we'd have to do a little bit of pH, pOH, or messing around with other stuff to figure out the other part of water's equilibrium and the associated hydroxide with an acidic system here. So what does that look like here? So here we go. There is your HCl. I've made it solid here just to help it cancel out of the problem without having to explain weird things. There's your liquid water. It's a strong acid, so the ionization that you see here is quantitative, no double arrow, but that doesn't matter for what we're doing. It's still messing with water, which is a secondary separate equation. There's the hydronium that would be taken, and there's the associated anion. This is what we did in Chem 20. Now, we get to learn this. We have 3.65 grams of HCl, and we have a 2-liter system of water. Yes, I'm applying it right here, but remember, these two guys are being mixed, dissolved, and ionizing. So when making an acid, you are dissolving a certain solute into a solvent, and the solvent and solution volumes are generally constant, like they are here. All right, by adding HCl to water, I haven't changed the volume of water. We're being asked to figure out the concentration in moles per liter of hydronium. Well, this just boils down to a stoichiometry problem. If I have 3.65 grams of HCl, I have dissolved this in 2 liters of water. Well, I have a concentration in grams per liter, but I need moles per liter before I can do my stoichiometry. So, if we take a look at the units that we have, grams can be canceled out with the molar mass value for HCl, and so for every 1 mole, this should be 36.46 grams. 35.45 from Cl, and 1.01 from the hydrogen. Grams now go, we have moles per liter, and we can solve the problem. In Chem 20, we realized that we could go moles per liter here in our acid system, so long as it wasn't a greater reaction, because the volume was constant throughout, so we didn't have to get just down to straight moles. Now I can take a look at my mole ratio, and you can see that it is 1 part hydronium to every 1 part HCl, which is typical for our strong acids. HCl now goes. I have moles per liter of hydronium here, and so when I run it through my calculator, I now have the concentration of hydronium, which works out to be 0.0500 moles per liter. I have fixed my sig-digs to be 3 to match everything that I have here, and now I have my hydronium. But the issue is, we're also looking for hydroxide. Now, we could go through hydronium to pH to pOH to hydroxide, but because we've introduced the equilibrium expression here, if you take a look at it, Kw here would be the concentrations of the variable reactants, H3O plus, and OH minus. Liquid would of course cancel. The solid HCl would cancel, so there'd be nothing for the reactants in the denominator, and this is our equation. Fill in your numbers that you now have. Kw is a constant. 1.00 times 10 to the negative 14 moles per liter. No units here. 1.00 times 10 to the negative 14. When we look at it at SATP, you have hydronium as 0.0500 moles per liter. Now that's fairly significant with everything we've learned in acids and bases. And then we just have the unknown of hydroxide. Okay, no problem. Simple math. Divide by the concentration of hydronium. Run that through your calculator, and the hydroxide concentration is resolved. All right, that gives us 1.0 times 10 to the negative 14 divided by 5 times 10 to the negative 2, which is a much larger number. We should end up with a very small value, and you get 2.00 times 10 to the negative 13. There you go. So this just becomes another, I like to think of it as a weapon to deal with all the pH, POH issues. All right. Not that big a deal. It's just another equation we can use. No different than your pH is equal to the negative log of hydronium, your pH plus POH is equal to 14, and your hydroxide ion concentration is equal to 10 raised to the power of the negative POH. So this just kind of simplifies some of these problems for us, or at least offers us another way through some of these various problems. It's just another easy equation to use. All right, we can take a look at one more here. That's question number 3. You have 1 gram of solid sodium hydroxide, which is solid, it's ionic, and it is added to 400 ml of water at SATP, so calculate hydronium and hydroxide ion concentrations. Okay, so very similar here, except we are dealing with an ionic substance of NaOH. All right, it is solid, and it of course would dissociate into the ions of Na plus and OH minus. I know you guys were all paying immaculate attention back in my Chem 20 classes in Chapter 6 when we were looking at this with acid solutions, but there is a subtle difference between what ionic compounds do when they dissolve, tough to talk today, and what molecular acids, our 6 strong ones, do when they interact with water. All right, there we go. So now we have that, and we have said that you have 1.00 grams of this stuff, and you have dissolved it in 400 mils, or 0.400 liters of solid, therefore solution. Okay, sodium we don't really care about, it's just an ionized metal. For pH and POH, we're more concerned with our hydroxide and hydronium, so we can go straight to there with our stoichiometry, since the balanced equation allows us to directly figure out hydroxide ion concentrations. Let's build our concentration equation, 1.00 grams of NaOH, and we have that over 0.4 liters of solution. This is a concentration in grams per liter, which is valid, but we need moles per liter to be able to deal with the stoich. So we take a look at our molar mass here, moles in the numerator, grams down below. 1 mole of sodium hydroxide weighs exactly 40 grams. The grams now go, and you have moles per liter of sodium hydroxide. Now you can do your mole ratio, because this was a simple ionic salt. All right, we ended up having 1 mole hydroxide for every 1 mole of NaOH that dissociates. That now disappears, and you have moles per liter of hydroxide. So we run that through our calculator, and you see you get 0.0625 moles per liter of OH minus. All right, so we've got that part. Now again, we could take this through the POH and pH plus pOH is equal to 14, and the concentration of hydronium ion, but we can also use now our new and updated equilibrium law expression for acids and bases and go straight to there. Kw is always equal to hydronium plus the hydroxide ion concentration. You can see that this is a solid. It would cancel out. These are the only two variable concentrations we have. So plunk in your numbers. 1.00 times 10 to the negative 14, since we're at SATP. We're looking for hydronium. And our hydroxide ion, we've just figured out, is 0.0625 moles per liter, which again is a fairly big number when we look at these solutions and water's equilibrium. So divide both sides by this big value. It cancels out, and since we're dealing with a basic system, we expect very little hydronium to be in this system, so hopefully this is a very small number, and when we do this, you can see that the hydronium is equal to 1.60 times 10 to the negative 13 moles per liter. All right, that last digit might be a little bit different. I've noticed here in my notes that I am dealing with a 2-digit answer, and the numbers in your calculation are 3. So if it does round to a slightly different one, don't worry about it. I think you can see what's going on. All right, here's the rest of it. Guys, please try 1 and 4 if you like. The answers are there. Go to the textbook, try a few from page 716, and get this new equation out of the way. In our next part of chapter 16, we'll review all of those pH, pOH questions and take this into some of the ice tables and see what this looks like when we get into more complex problems dealing with weak acids that don't ionize completely.